So I'm delighted to talk to you today about some of the things that are happening in machine learning. I think it's a pretty exciting field. And I'm going to talk to you about some work that I've been involved in, but also some work that some of my colleagues have done. It's the work of many, many people at Google. And it's my delight to present it to you. So a couple of observations, three actually. So you've probably noticed that sort of machine learning has been making steady progress over the last kind of decade or so. And it's really, I think, gotten to the point where it's now changed what we expect a computer to be able to do. You know, maybe 5 or 10 years ago, you didn't really expect a computer to understand, what's in an image, or, the speech recognition kind of was there, but it really had lots of errors in it. And now we're seeing that, computers interacting with kind of natural modalities that people are sort of familiar with can be much more fluid and natural. A real lesson about machine learning in the last decade is that increasing scale, both the amount of data you train on, the generality of the data you train on, and the model size, and applying larger scale compute really tends to deliver better results. And that's been true as we increase the scale kind of every year or two, we kind of move up another level in the scale ladder, and that has not stopped working yet. It may at some point, but for now, increasing scale gives better results. And it's also kind of changed the kinds of computations we want to run on computers. And so it's really thinking about new kinds of hardware that are really well suited for the kinds of machine learning computations we want to run. So just to give you a sense of things that computers can now do that they didn't used to be able to do. So image recognition is a common thing. You have some set of categories of objects, maybe it's 1,000 categories, maybe 10,000. You can feed in the pixels of a raw image, and you can get models that will now give you a pretty accurate prediction of what's in that image. Audio, this is sort of speech recognition. You feed in raw audio signals, and you can get a transcript of what's being said. Translation's been around for a long time. Hello, how are you? And you get the French sentence. And you can even feed in the pixels of an image and get not a categorical label, but actually a short sentence describing that scene, basically. But perhaps even more surprisingly, in the last few years, we figured out how to reverse all these errors. And that's pretty amazing, right? Now you can go from a category like leopard, and a model can generate you 100 pictures of a leopard. Or you can go, text-to-speech has been around for a while, but it's gotten much, much better in quality. So you now have very realistic sounding human voices. Translation of the other direction is maybe not that interesting. But you can also write short sentences, and the model can generate images that are faithful to all the details represented in that sentence. So I think this is pretty amazing. Like, this is really transforming what you think of computers as being able to do. And you've seen this is steady progress in a bunch of different academic benchmarks. So ImageNet is this image classification task that a bunch of people at Stanford University put together this nice challenge in 2011 with 1,000 categories of objects, and then you have a bunch of images labeled. You can train on those images, and then there's a test set of images your model has not seen, and you have to make the prediction of which of the 1,000 categories is this. It's actually pretty hard because there's, like in those 1,000 categories, there's 45 breeds of dogs or something, and most humans don't actually know all the breeds of dogs. So in 2011, the first year of the contest, the winner was 50.9% accurate. Then the next year it was held, AlexNet, which was a famous paper by Ilya Sutskever, Alex Deshevsky, and Geoffrey Hinton, made a huge leap in accuracy. This is a quite significant leap in computer vision. And they were the only folks that used a neural net that year. The other 27 entrants did not. They were using more classical computer vision techniques. So the next year, 27 of 28 entrants used neural nets. So because of that giant leap. That's really pretty remarkable shift in a thinking of a field that's been around for a while. It's also important to point out the progress has not stopped there, right? Like, this was a major leap, but since then, we've gone to above 90% accuracy on this pretty hard task. You see a similar trend in speech recognition. This is actually a bit shorter timescale, so this is only like 5 years. We've gone from 13.2% accurate word error rate down to 2.5, which is great. 13.5% error rate is, kind of not very usable speech. Every sixth word or eighth word, you have to like fix something. Now it's every 40th word. And I said one of the trends was that every time we scale, we actually get better results. And so it's actually changing the way in which you want to design computers so that they're more suited for the kinds of computations we want to run. So if you optimize the hardware for machine learning, you actually can be much more efficient, and I'll describe why. There's been major improvements from generation to generation. You see this in sort of more modern GPU generations get considerably faster than the previous one. And this enables larger scale models, but also makes them much more economically affordable to train and significantly lower energy costs than if we were using non-ML focused hardware. So these algorithms tend to have two properties that are really, really important for designing hardware around them. One is that neural nets tend to be very tolerant of reduced precision. In fact, some training techniques you actually want to add a little bit of noise to the training process in order to sort of get them to perform better. So that means you don't need to carry out computations to 6 or 7 decimal digits. You can just carry them out to 1 or 2 decimal digits. And that's really nice from a hardware perspective because all of a sudden you can pack like 10 multipliers in the space you would have had to put 1 or 2. And the other thing that's nice is most of the algorithms are just different kind of configurations and orderings of different kinds of linear algebra operations, matrix multiplies, vector operations, things like that. And so if you can design computers that are very specialized for those, things that have like systolic arrays to do 2D matrix multiplies in like single clock cycles, that enables you to build reduced precision linear algebra hardware, essentially is what we're really building. And that really accelerates the machine learning computations. We've been doing that for a while at Google. We've actually got a series of processors called tensor processing units. The first one came out in 2015 and was really designed to enable us to actually deploy these neural nets in computer vision and speech recognition in a way that made it actually affordable to do that. If we didn't have these, we would have had to actually double the number of computers we had in our data centers just to deploy a more accurate speech recognition model. But this made it so we could put a few racks of these things in different data centers and it was all fine. Then subsequent generations kind of tackled hardware for not just inference, but for training. And so these are really part of a much larger system. You can think of them as sort of supercomputer-like systems composed of these boards and chips. V2 is there, 4 chips on that board. V3 is there. That adds liquid cooling to the surface of the chip, which is always exciting. V4 has liquid cooling as well, but now colored wires. Pretty great. And these are designed to be connected together into larger configurations called pods. And so essentially they have customized networks that are very high speed, but not very flexible. So essentially each chip is connected to its neighbors. In V2, it's a 2D configuration, so you're connected to the north, south, east, and west neighbors. And in V4, it's actually a 3D torus with a kind of funky rack level reconfigurable fiber optic thing, so you can sort of make Lego blocks of different shapes of racks, a 3x4x4 configuration of racks, or a 2x16x16 if you want, things like that. And then V5, which we just announced towards the end of last year, is actually even larger configuration. So the V4 had 4,000 chips per pod, and the V5 has close to 9,000 chips per pod, and gives you 4 exaflops of reduced precision computation. Okay. Then you've probably noticed there's been a huge set of advances in language modeling. And let me just talk through some of the important things that have been happening in that time frame and why we are where we are. So I started getting interested in language modeling when some of my colleagues in the Google Translate team said, oh, we have this really amazing algorithm, but it's really slow. It takes like 6 hours to translate one sentence because we need to do 400,000 disk seeks in order to like look up all the language model statistics in order to do the translation. I said, well, that seems a little long. Why don't we put it all in memory and design a little custom data structure for it? So that at this time, we actually trained a 2 trillion token n-gram model with 5 grams. So we kept statistics for all 5 word sequences that occurred in those 2 trillion tokens. And then you could do lots of lookups and sort of use that in translation. We had big boosts in translation quality because now our language model gave you a better sense of like, is this a plausible phrase of words or not? Then one of my other colleagues, Tomasz Mikolov, a few years later, was very interested in distributed representations of words. So he developed this nice algorithm where you could sort of have a dense vector represent the kind of meaning of a word in some sense. And by understanding the context in which a word occurs, you could nudge it in certain directions and away from other directions. And you end up with these dense vectors in some high dimensional space, like maybe 100-dimensional or 200-dimensional vector. And what starts to emerge from the training process is all the words that are nearby in this vector space tend to be very related. So, king and regent or things like that. But even more interestingly, directions in this space are meaningful. So if you're at the point king and you go in the direction to get to the point of queen in this 100-dimensional space, it turns out that's roughly the same direction you go to get from man to woman. And similarly, if you go in a different direction, you get from the present tense of a verb to the past tense for almost any verb. And so that says that there's actually a lot of rich information in both the positions of these points and also the arrangement that they have together, which was pretty nice. Then 3 of my colleagues used an approach of a kind of deep neural network that was a recurrent network to train what's called a sequence-to-sequence model. So now you have a model that is an encoder. So it's trying to absorb a word of input at a time and update a representation for every word that it sees, and to get to a representation that it's now going to use to initialize a decoder. And that initialization of the decoder then is going to go one step at a time and make predictions of what words should be decoded. And it turns out you can basically take training data for machine translation, an English sentence and a French sentence, stick them back to back, and train the model to, when it sees this English sentence, to then decode into this French sentence, and train this over and over on lots and lots of aligned sentence pairs like that. And you get a very high quality translation system. And this sequence-to-sequence approach turns out to be useful for a whole bunch of other things. In particular, Oriol and Kwok then went on to realize that it could be used in a kind of multi-turn dialogue system. So there, the context that you're encoding is kind of the previous part of the conversation, and then the decoding you're doing is like, what should be the response now that you're at turn 6 of this conversation? You've previously said, how's the weather today? Oh, it's great. I really like being here in Mysore, and I enjoyed lunch. What should the output be now? And it can actually make a good prediction of that. Then another set of my colleagues developed a technique called the transformer model, which instead of these recurrent models where you essentially have some representation and every step you're updating that representation. The problem with that approach is you now have just a single representation, and you have this very sequential process of absorbing a token at a time or a word at a time and updating it. And so my colleague's insight was essentially, why have this recurrent thing at all? Let's just save all the states that we've seen and then pay attention to the history of states when we're trying to make a future prediction of like what word should we emit now. And that was really nice because now you can process all the context in parallel rather than having this sequential step of a recurrent network absorbing one word at a time. And it gives you this ability to attend to anything that seems to make sense to the model. And you can train the attention mechanism to pick up on things that are important for the things you're trying to train the model to do. So then some of my colleagues then worked on a transformer-based neural chatbot, so follow-on work from the earlier one that was using LSTM. And one of the things they discovered was scaling up and training on conversational style data really gives really good results, significantly better than previous chatbots simply because of the scale and the type of data they trained on. And then there's been a whole progression of really nice, essentially scaling of language models that are more and more powerful. So OpenAI published a paper about GPT-2, first sequence to sequence and then transformer were demonstrations of significantly better language models than GPT-2, T5 by some of my colleagues at Google, GPT-3, Gopher, Palm, Chinchilla, Palm 2, GPT-4, and most recently, I've been co-leading a project called Gemini, which is a bit more than a language model. We've made it a multimodal model. We started this project in early February last year, and it's a very large-scale project. It's a lot of machine learning is now moving into the vein of kind of large-scale science. So I'm now a co-author on a paper with 900 co-authors, which is exciting. It's not quite physics level, but it's getting there. And our goal was really, how do we train the world's best multimodal models and use them all across Google? And so we wanted this model to not just know about language from the beginning, but to know about language and images and audio and video. And that gets turned into a sequence of tokens, fed into a large transformer model, and then we have outputs for image decoders and text decoders, and we can bolt on an audio decoder after the fact. And we have several different sizes of this. So the Ultra model is the largest one that we trained. Pro is kind of the workhorse one that we deploy in our data centers. And then we have nano ones so that they can run on a phone because oftentimes you want sort of machine learning algorithms to be able to run locally, run very quickly, run on small devices. One of the pieces of infrastructure that we use for training Gemini models and earlier models is a system called Pathways that I worked on with a bunch of colleagues. Really, this is a kind of a level of indirection for how do you express machine learning computations, and then how do you map them onto a bunch of computational hardware that the system gets access to. And here we have a kind of nice abstraction where you can say, I'd like this part of the model to run on 1,000 chips somewhere, and this other part to run on a different 1,000 chips. And then the underlying pathway system is responsible for, okay, I have these hardware available, I'm gonna put it on here, and I'm put this other part on here. And then it manages all the communication between the pieces of the model you're trying to train. So if communication is local, it'll use the very high-speed network in one of these pods. We can actually span pod boundaries and train on multiple pods. And in that case, it falls back to using data center network transfers and other transport substrates. So one of the things about training at large scale is these failures become more common because as soon as you have tens of thousands of chips operating, some of them are going to fail sometime in a many-month training run. And so minimizing failures is really important. One way to do that is just don't do stupid things to yourself. So like instead of allowing kernels to be upgraded kind of randomly in your job, and that sort of takes one of the machines down, and then you're like, oh, well, we better restart the job. And then the next kernel gets upgraded. You sort of coordinate that in a bit more organized fashion. A lot of other Google services are such that they're not all these interconnected systems. They're quite so tightly coupled, and so it's perfectly fine to upgrade kernels randomly, but not our job. But you also want to minimize the time to recover. And so one of the things we did was, we have many actual copies of the parameters of the model we're training on different pods. And so when some machine on some pod fails, we actually can just recover from memory from the other chips in the system. And that makes recovery, take a matter of a few seconds instead of several minutes, which is quite nice. And therefore, although we used Pathways for training the earlier Palm model, at a much smaller scale, which it was getting 85% goodput, which is sort of the fraction of time you're actually making positive forward progress rather than recovering from checkpoints or something. We actually got to 97% goodput for the largest scale training, even though it was a much larger scale run. For training data, it's really important to have a broad range of different kinds of data. The more sort of general world knowledge you can put into the system, the better it'll be able to handle lots of kinds of questions. So we trained on a bunch of web documents and books and code, but also kind of multimodal data of various kinds. It's important to kind of filter your data sets in various ways. We have some heuristics and some model-based classifiers that say, yeah, I think this is a high quality document or not so high quality. The actual mixture of what proportions of these things to use, we determine through ablations on small models, looking at results on a bunch of different benchmarks. Should we use 32% code, which would give us better performance on coding benchmarks, and how will that hurt, multilingual performance versus if we did 26% code and 31% non-English data. But really, it's definitely the case that the quality of the data you train on is really critical for a highly performing model. And so I think there's a lot of interesting work to do there of identifying really high quality data, generating and synthesizing perhaps synthetic data to train on and so on. Another thing that's been shown to be the case in the last few years is the way in which you ask a question of the model actually has a big impact in how effectively it can answer it. And so some of my colleagues invented a technique called chain of thought prompting. So in standard prompting, you kind of give the model an example of the kind of question you're going to give it. You're going to try to ask it and the answer, and then you ask it the question you'd like it to really answer, and it will sort of follow this pattern. So it now says, here's one problem with the answer. Here's the problem I really care about, and the answer is 50. It turns out to be wrong. But if you encourage the model to show its work, sort of like your 4th grade math teacher encouraged you to show your work, it not only will follow that pattern when it's answering the question you really asked it and show its work in these intermediate steps, it's also more likely to get the answer right. Which is quite nice. And this actually has a pretty dramatic effect. So this is the same model, and the only difference is whether you use chain of thought prompting in the pink or you didn't in blue. And you see that really dramatically improves the quality of answers in a couple of different mathematical benchmarks. Then evaluating how effectively you've trained your model is a pretty difficult task. You want to identify what's the model good at, what is it not so good at. You want to do this throughout the training process so you can understand, is our math performance where we would hope it would be, or should we think about interventions, like maybe we should add some more math data to the mix of data we're training on. How do we compare the capabilities of our model to other models, and so on. So our eval team in Gemini did a huge amount of work, and you'll see in the next tables how well we did. But basically, we were able to train a model that exceeds the performance on 30 of the 32 widely used academic benchmarks, which is we were pretty happy about. So if we look at just some of them, these are sort of textual related benchmarks. There's one called MMLU that is a representation of questions across 57 different areas of study, everything from science and chemistry and so on to international law, humanities, philosophy. And we got a score of 90.0, which is nice. That 90 is circled there or highlighted because human expert performance on these tasks, on that task, is 89.8. We were pleased to slightly squeak by that. And then we achieved state-of-the-art performance on 7 of the 8 of these benchmarks. If you look at image understanding benchmarks, the Gemini Ultra is the best performing model that we know about. Similarly, for video understanding, these are a whole bunch of different video understanding benchmarks. And similarly for audio, like speech recognition and speech translation, as well as multilingual benchmarks. So this is like really nice documentation of the performance on a bunch of academic benchmarks, but it's also just better to see what the model can do and why that's exciting, I think. So One of the nice things is Gemini is multimodal, so you can give it something that's both text and visual, kind of draw this hand-drawn diagram in kind of fairly readable but slightly sketchy to read handwriting. And so here it is. A skier slides down a frictionless slope as shown. What's the skier's speed at the bottom? And then the solution that a student has worked out. And it says, try to reason about the question step by step. So there's your chain of thought prompting. It says, please tell me what you're doing. And did the student get the correct answer? If the solution is wrong, please explain what is wrong and solve the problem. And make sure to use LaTeX. We're going to use LaTeX. And round off the final answer to 2 decimal places. And so this is the output. Says, sorry, the student didn't get the correct answer. They made a mistake in the calculation of potential energy. Start of the slope was given by MGH, but the student used the length of the slope instead of the height. And there's the correct solution at the start of the slope, blah, 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 blah. They used LaTeX, which we rendered in the answer. So pretty cool. And there's the answer in 2 decimal places. And you can see how this would be really, really helpful for a lot of educational settings. The fact that you can feed it images of text or just regular old text or audio. And it's surprising how coherent conversations can be. So for example, this is for a talk I was giving about 6 months ago. I asked Bard, which is our product through which we surface conversational agents, could you please reverse the letters of Hot Chips and Tensor Processing Unit for me? This is for a Hot Chips conference talk. And it said, sure, here's the reversed strings. Great, that was helpful for me. But it also then went on to say, I can do this for you in Python, and here's the code. So there's the code. And then it goes on to explain the code. It says, hey, the first function defines reverse string, takes the string as input, returns the reversed one, it then prints it. Is there anything else I can help you with? It's always nice to be polite at the end. And so then I said, tell me more about TPUs. And it has a fair amount of world knowledge. And so it said, sure, tensor processing units are this. They're specialized hardware processors developed by Google to accelerate machine learning. They can help improve the performance and efficiency. So that's kind of nice. And then we've actually just put the Gemini Pro model, the medium scale model, into our Bard product. And there's an external organization called LMSys that has a chat arena evaluation mechanism where they essentially pit 2 randomized chatbots head to head. A user can enter a prompt and then see 2 responses and then vote for which is better. And they don't get to see which chatbot it is. And then from that, you can compute what's called an ELO score, which is a way of ranking participants in tournaments that's used for chess, for example. And an ELO difference of roughly 100 means the higher scored participant would win 64% of the time. And so with our medium scale model, we debuted at the 2nd spot on this leaderboard, which is pretty nice, behind only GPT-4 Turbo. We're pretty excited about our Ultra model, which is getting ready to be put out in the world. So I tweeted about this. I do have social media. And then this person who I don't know followed up and said, it's really pretty good. Check out this example. Bard allows you to share interactions you had that you found interesting in some way. So I clicked on it. And this person asked them, please estimate the number of companies per million residents in each of the following countries: US, England, South Korea, Taiwan, and Singapore. Present your number in table form. And absolutely, Bard's ever enthusiastic. Here's a table showing the estimated number of countries. As you can, and then explain it. England has the highest number of companies per million residents, actually by quite a bit, surprisingly. And then this person went on to say, where did you find the numbers? And it says, oh, I apologize for not providing sources. It's important to be transparent. So the data I used came from a combination. I used data from Dun & Bradstreet for the US. I used data from ONI. So it's pretty nice. It's pulled information from a bunch of places, done something that would have taken you, 15, 20 minutes in, one response and one interaction with it. I hope this information is helpful. Please let me know if you have any other questions. So I think this is kind of a pretty cool future. It's going to be good that it can do all these kinds of things that would normally take you a lot of time. And a further refinement of general models can make these amazing domain-specific models. So some of my colleagues have been training more medical-focused models, starting with these base models. So they started with the PALM model there and found that it could score above the medical board's passing exam for doctors. And then when you trained it on PALM 2, which is a much more powerful, better language model, they got to an 86.5% score, which is actually expert doctor level passing of the medical boards. And another trend is that the outputs of these models when you generate images or other media is pretty startling and amazing. So we had two projects, Party and Imagine. They've now merged together into one that were trying slightly different techniques for generating images. But these things can take prompts like this. A steam train passes through a grand library, oil painting in the style of Rembrandt, and sure enough, there you go, pretty good. A giant cobra snake made from X, where X could be corn or pancakes or sushi or salad. A photo of a living room with a white couch and a fireplace, abstract painting, and light comes through the window. That's nice. And, it can actually be quite detailed, right? High contrast photo of a panda riding a horse, or wearing a wizard hat, blah, blah, blah. There's a book, standing on a street, gray concrete wall. There's some word piece behind them, green grass, DSLR photograph, daytime lighting. And it can mostly do that. That's pretty faithful. There's obviously a lot of degrees of freedom. We could have picked, a different color horse or whatever, but there's, it does adhere to your prompt. And we actually just put this in BARD as well. So now you can prompt BARD and ask it to generate images. The government of Illinois K through 12 education system is very excited that we could render their mascot, Hyperlink the Hedgehog, for them. And this person was very excited because they asked them to draw a human buying coffee at Costa Coffee in London, and it actually got the text right. One of the shortcomings of most of these generative models in recent past has been they can't really render text very well. And part of that just comes from scaling and fidelity of the model. So this is basically how the Imagine model works. You basically put in text, you get one of these dense representations to initialize the decoder for the images. So now we're decoding images instead of decoding text. And from that text embedding, you generate a small scale image. And then there's a model that's been trained to increase resolution and to increase resolution again. So you go from small scale thumbnail to bigger, and that's all conditioned on the text embedding that you've conditioned, that you've sort of held fixed. And you really see the effects of scale here. So if you train 4 different models of this approach, one of them is 350 million parameters and less training time, and then you just kind of scale it up. And then you ask each of these versions to do that prompt, portrait photo of a kangaroo wearing an orange hoodie and blue sunglasses. So it kind of understands orange hoodie and blue sunglasses, but not much else at the scale. And the text is like completely unrelated to what it was asked. So now it kind of knows about Sydney Opera House a little bit, but it's still kind of blocky. That's now a much better representation of Sydney Opera House. And now it's gotten nice, crisp Sydney Opera House. And the text evolution is also quite startling. At 20 billion, it does exactly what you wanted with the right text. Here or here, not so much. And that's essentially the same story in graph form. And I think it's also really cool how many different fields are now adopting these tools and understanding how they can be used to solve all kinds of different problems in engineering. Pretty much every field of science is looking at how can machine learning be used in different subproblems, health, sustainability. I'll just highlight a couple of things that some of my colleagues have done. So one issue is in many parts of the world, there aren't really good maps. Even Google Maps is missing a lot of buildings in many parts of the world. And so some of my colleagues worked on some work that can identify buildings from satellite imagery. And it's actually harder than it looks because none of these images have any buildings, even though at first glance they do look like they might, because there's like pools and rocks and enclosure walls and shipping containers, not buildings. But with the right training data and the right kind of focus on that problem, you can actually identify building boundaries pretty well. And then you can partition and segment them and identify which ones are the same building, which ones are different. And initially, this team was based in our Accra research office in Ghana. So they focused on identifying buildings in Africa. They found 500 million buildings that we didn't know existed before in our maps. And then they've since expanded to cover most of the global south, including India, Southeast Asia, Latin America, and the Caribbean, and found 1.8 billion buildings to increase coverage of maps in lots of places. It's pretty cool. And there's huge opportunities in medicine. You know, the MedPalm work, where you can now have an expert kind of doctor level conversation agent, but also in medical imaging and diagnostics. So we've been working in many different sort of sub areas of this problem. One of the ones we've been working in the longest is diabetic retinopathy. So we've actually been able to detect diabetic retinopathy better than expert ophthalmologists. And we've actually got this deployed in many places, including India first. So we actually made a partnership with a Indian eye hospital, set of Indian eye hospitals, Aravind and Sankara Eye Hospital Networks. And then it's also been deployed in Thailand and France and Germany. And then DermAssist is actually an on-device machine learning model where you can take a picture of something where you are not sure is that benign or malignant, and it can actually give you kind of a better than dermatologist level of categorization of like, yes, you should go get that checked, or no, you're probably fine. And then because these tools are going to be used in lots and lots of important ways in society, in all different settings, it's really important to have a set of principles by which you think about, is this a good use of machine learning? Are there things I should be worried about or consider in how I think about putting these things out into the world? And one of the things that we did as a company is in 2018, we came up with a set of principles by which we look at all uses of machine learning in our products and in the research that we do. And I like these principles. They haven't actually changed because they've actually stayed true since we made them. We published them publicly because we thought it would be helpful for other organizations who are starting to think about, how should they be using machine learning. And I'll point out that if some of these areas are kind of active areas of research in the field of machine learning. So how do you avoid bias in machine learning models? Many of the techniques we have are okay, but there are better techniques to be discovered. And so we've basically, you want to use the best known technique at the moment, but you then also want to strive to come up with better techniques. And there have been 200 Google research papers since 2018 related to some of these topics. So it's definitely a pretty important and active area. All right, and with that, I am done. I think it's really important to understand that we're seeing major progress in what computers can do from machine learning. And as we scale these models up, as we make them understand more modalities of things, as we make them able to sort of better do multi-step reasoning in solving problems, as you saw in some of the examples, that really changes what you think of as possible for computers. They used to be kind of these tools you could use for kind of each step of something you're trying to do. Now they're things that can do many steps for you in one sort of well-crafted request. And I think that's going to enable us to do all kinds of amazing new things. But there's also a lot of responsibilities of how do you get these things out into the world in a way that is, world positive and good.